Welcome to our review of vectors. In mathematics and physics, vectors are incredibly important tools that help us describe quantities that have both magnitude and direction. Let's start by visualizing what a vector actually is. Here I'm drawing a vector as an arrow. The length of the arrow represents the magnitude or size of the vector, and the direction the arrow points represents the vector's direction. There are several ways to write vectors mathematically. The first and most common way is in component form. For a two-dimensional vector, we write it as v equals angle bracket v sub x comma v sub y angle bracket, where v sub x is the horizontal component and v sub y is the vertical component. Another way is to write it in column form as a matrix with one column and two rows. And of course, we can represent it as an arrow from the origin to the point v sub x, v sub y. Let's look at an example. Vector at equals angle bracket 3. For angle bracket, this means the vector goes 3 units in the x direction and 4 units in the y direction. It's an arrow from the origin 0, 0 to the point 3, 4. Next, let's talk about the magnitude or length of a vector. The magnitude of a vector v is denoted by 2 vertical bars on each side, and it's calculated using the Pythagorean theorem. For a 2D vector, v equals angle bracket v sub x, v sub y angle bracket, the magnitude is the square root of v sub x squared plus v sub y squared. Let's use our example vector at equals angle bracket 3. For angle bracket again, the magnitude of it equals the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, equals the square root of 25, which equals 5. We can visualize this using the Pythagorean theorem. The vector forms the hypotenuse of a right triangle, where the other sides are the x and y components. Let's move on to vector addition. When you add two vectors, you add their corresponding components. For vectors u equals angle bracket u sub x, u sub y angle bracket, and v equals angle bracket v sub x, v sub y angle bracket, their sum is u plus v equals angle bracket u sub x plus v sub x, u sub y plus v sub y angle bracket. Let's look at an example. If u equals angle bracket 1, 2 angle bracket, and v equals angle bracket 3, 4 angle bracket, then u plus v equals angle bracket 1 plus 3, 2 plus 4 angle bracket, which equals angle bracket 4, 6 angle bracket. Geometrically, we can visualize vector addition using the tip-to-tail method. We place the tail of the second vector at the tip of the first vector, and the sum is the vector from the tail of the first vector to the tip of the second vector. Next, let's discuss scalar multiplication. When you multiply a vector by a scalar, a regular number, you multiply each component of the vector by that scalar. For a vector v equals angle bracket v sub x, v sub y angle bracket, and a scalar k, the product k times v equals angle bracket k times v sub x, k times v sub y angle bracket. Let's look at an example. If v equals angle bracket 2, 5 angle bracket, and k equals 3, then 3 times v equals angle bracket 3 times 2, 3 times 5 angle bracket, which equals angle bracket 6, 15 angle bracket. Geometrically, scalar multiplication stretches or shrinks a vector, and if the scalar is negative, it reverses the direction. Here, multiplying by 3 makes the vector 3 times longer but keeps the same direction. Now, let's discuss the dot product, which is an operation that takes two vectors and produces a scalar, a single number. For vectors u equals angle bracket u sub x, u sub y angle bracket, and v equals angle bracket v sub x, v sub y angle bracket, their dot product is u dot v equals u sub x times v sub x plus u sub y times v sub y. Let's look at an example. If u equals angle bracket 1, 2 angle bracket, and v equals angle bracket 3, 4 angle bracket, then u dot v equals 1 times 3 plus 2 times 4, which equals 3 plus 8, which equals 11. The dot product has a geometric interpretation. It's related to how much two vectors point in the same direction. Specifically, u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between them. Briefly, let's mention three-dimensional vectors. A vector in 3D space has three components x, y, and z. We write it as w equals angle bracket w sub x, w sub y, w sub z angle bracket. The magnitude of a 3D vector is calculated similarly to a 2D vector, but with the z component included. Magnitude of west equals the square root of w sub x squared plus w sub y squared plus w sub z squared. Here's a simple visualization of a 3D vector. All the operations we've learned, addition, scalar multiplication, dot product, extend naturally to 3D vectors. Let's summarize what we've learned about vectors. A vector is an arrow with both length, magnitude, and direction. We typically write vectors in component form. Angle bracket v sub x, v sub y angle bracket. The magnitude of a vector is calculated using the Pythagorean theorem. To add vectors, we add their corresponding components, which geometrically corresponds to the tip-to-tail method. When multiplying a vector by a scalar, we multiply each component by that scalar, which changes the vector's length and possibly its direction. The dot product gives us a scalar that represents how much two vectors point in the same direction. These basics will help you work with vectors in physics, geometry, and many other fields. Thanks for watching.